All right, so it's 9:30, and let's go ahead and start the next section. In this section, we're going to start the portion that introduces deep learning and start picking up the pace and from a technical perspective a little bit. Um, so one question to start off with is, what is deep learning? Well, if we consider artificial intelligence in general, with the idea that this is programming systems, automated systems with the ability to learn or reason like humans do, then a subset of that would be algorithms that don't have to be explicitly programmed, often using some sort of statistical method. This is machine learning. This is where we train the systems to identify patterns within the data, and then those patterns can be applied to data sets afterwards. Deep learning then is a subset of machine learning, where the systems, it involves a particular set of methods using artificial neural networks, often uses very large amounts of data. So this will be the discussion that we'll be having today. Because it requires some specific methods and also requires sometimes requires very large amounts of data, it's worth motivating why are we interested in deep learning. There's a couple of different reasons. One of them has to do with the ability to model a task from end to end. Here's an example of a document classification task. Let's say we're trying to classify whether a document refers to COVID-19 or not. Obviously, this is a very timely and important task at the moment, but in general, document classification is extremely important. Databases, for example, have to determine whether a document is curatable and relevant to the scope of the database, for example. Before they apply text mining and to it, or spend any time with human expert curators. Under traditional machine learning, while it does have the advantage that it doesn't have to be explicitly programmed, it does have to have explicit feature extraction, which is where a human writes some amounts of code that allows particular inputs to be represented numerically in a way that the classification algorithm can then access it. And this has two disadvantages. One of them is, well, you still require an expert to apply it, but also that is the only representation that the classification method can then access. With deep learning, you have the ability, you do a bit of a trade-off. Well, it does often require more data and definitely more compute, servers which can handle significant higher loads and also graphical processing units. You have the ability to you do away with this feature extraction step, because the deep learning itself will then extract the features for you, so that it then will learn very nearly end to end the task that you give it. And partially as a result of this, it has a tendency to continue learning as you give it more data. Under classical, typical machine learning methods, they tend to fairly quickly get to a point where more training data is not providing additional performance gains. While deep learning methods, they do tend to level off a bit, but don't reach a plateau quite as quickly. And certainly even the largest models, while they're very compute hungry, tend to continue learning as long as you are willing to continue training them. So to start going into the technical aspects of what exactly is deep learning, we're going to go through a simple neural network setup. And to try and make it just a little bit concrete, we're going to set up a particular problem, specifically document classification. For example, we have an input where a specific document, and for right now, we're going to still need this intermediate representation. These features, you could consider, for example, a 1 or 0 feature, whether the text COVID-19 is present in the document, would be a very obvious example of a feature that would be useful. Publication year is slightly less obvious, but obviously if a publication was published before 2018, it's not going to be, it's not going to mention COVID-19. So, so here are a couple examples of new features, numerical features that could be used. There are quite a few of these, but in a later section, we will set aside the need for features, but for right now, we have something concrete we can keep in mind. So this set of features, we're going to use this as a real valued vector of length n, x. We have an output for any individual document. Either it's going to be relevant and related to COVID-19 or it's not. So 0 or 1. And our system's job then is to give a prediction. The probability that y is equal to 1, that is the probability that this document is related to COVID-19 given a specific set of features that represent that document. And so our job is to build a function f here that will then give this, excuse me, that will then perform this perfect prediction for us. So restating the problem slightly here, let's see if we can start off with a linear function. One moment. So a linear function is more or less the simplest thing we could possibly do. So let's start off with that. And what we're going to do is we're going to introduce a set of parameters. The w is a vector of the same length as x, the same number of features. And we're going to do a simple linear transform here. This is an affine transform. And we're going to add a b parameter where it crosses the origin. And let's ask ourselves if this will be enough for us to be able to perform classification. And there's a problem with this where the output that we're looking for is a probability. So it's between 0 and 1. And while this gives us some weights, and it does not limit the value, the resulting value to 0 and 1. So what we're going to do for that is we're going to take this function, we're going to run it through a sigmoid. Sigmoid has this this form that you can see here. Well, it looks a little complicated. It actually has some aspects that are simpler that we'll be taking advantage of later. But mostly, the nice thing about it is that it gives an output that will always be between 0 and 1, no matter what value we introduce. And we can also simplify this a little bit by defining that the input features, the 0th feature always has the value 1, no matter what the document is. And if that's the case, then we can get rid of this b parameter because that will then be the 0th weight in our w vector. So looking at this setup, assuming we have a appropriate weight vector, we now have the ability to set up predictions. But one way of looking at this, rather than the mathematical view, is to look at it as a simple neural network, which it is. You can see we have a layer here. This is the inputs with the x's, and then we are able to pull them together using the weight vector, and then we run that through the sigmoid to get our prediction whether or not our document is related to COVID-19 or not. So the next question is, how do we train this? How do we find a W value that that allows us to get good predictions? And we're going to make use of our training data. So we need a set of data points where we have both the input is known, the set of features, and then also the value whether that particular document is related to COVID-19 or not. Each of those Ys are 1 or 0. And we need then, this turns the problem into finding the set of parameters that best fits this, this data set. So we can, what we then need to do is formalize this idea of fitting. And with deep learning and with machine learning in general, we turn this into an optimization function, an optimization problem. So we use something called a loss function, also known as a cost function. And the for a given data point where we have the features and we have the known value of whether or not this is related to COVID-19, and then we can use our current set of parameters to give a prediction. From there, we apply the loss function to identify how badly are we wrong. The loss function that we're going to use for this problem is the one that's listed here, which again, it's piecewise and looks complicated, but basically what it means is that if the document is related to COVID-19, this is the blue line. Basically, if we're giving a low probability that it's related to COVID-19, then we have a high loss or a high cost. And if we predict that it's highly likely that it's related to COVID-19, we have a very low cost. And then vice versa for documents that are not related to COVID-19. And if we look carefully, since Y is either equal to 1 or 0, we can actually remove the piecewise aspect by multiplying each of these elements by the value that we're supposed to be predicting to get a single function that then will give us the loss for any particular XY pair. So now we have the ability to tell us how far we're off for any particular single data point. What we need now is an algorithm that allows us to then iteratively improve our predictions. And what we're going to use is stochastic gradient descent. Basically what this means is that for each of the data points, we're going to identify the loss, and then we're going to find the gradient of that loss. That is the partial derivative, so that we can look at to see where which direction we would need to go in order to reduce the loss. That is, and then adjust the weight vector towards that lower loss. And then what we'll do is we'll repeat that process for every data point, and then perhaps multiple times through the data set to iteratively improve the weight vector until we reach a point with the minimum cost. So, my system is notifying us that we have several different comments happening in the chat, but it's not showing me what the chat is.
So Robert, it's about, they are asking for getting the PDF version of the presentation. So we already responded. So we are monitoring, we'll let you know.
Great, thank you. Okay, appreciate that. We'll just go ahead and continue then. So then for each of the training data points, the gradient actually has this very simple this simple form here, which is an advantage of using that particular loss function, so that then all we have to do is multiply this gradient vector, which is tells us which direction will have the lowest cost, by a small amount, the learning rate, so that we can then take a small step in the direction of changing our weight vector towards having a lower loss on that data point. We iterate that again over the entire data set of training points that we have, and perhaps multiple times through the training sets. Then what this will do is it will iteratively make improve any weight vector that we start with towards the minimum cost. So far, we've been talking about just having two separate classes. The example we've been using is a document relevant to COVID-19 or not? More typically, we have a case where we have many different classes. And so this will be the first extension that we'll be applying. In this case, the input would be the same, but the output, rather than being just a simple 0 or 1, it's going to be an m-dimensional vector where essentially it's what we call a one-hot vector. That is, only one of the m values is going to have the output 1, and all of the other ones will be a 0. Our prediction, rather than a simple 0 or 1, will be, again, if we have m different classes, we'll be predicting a 0 or 1 for those m classes. This is a probability vector where the sum of all the probabilities is equal to 1. And we can actually reuse most of what we've created so far in order to do this. For two classes, we use an n by 1 parameter vector, w, and for m classes, we're just going to introduce extend that so that it's instead of a vector with just one, instead of just being a vector, it's going to be an n by m matrix. The equation has a very similar form. We can, again, just do the affine transform, but because with two classes, we use the sigmoid. With m classes, we use we use what's called the softmax. Softmax does basically what it says, which is it tries to give most of the weight to the item that has the largest value. So we'll by doing this multiplication, we'll have m different values. What it will do is exponentiate each of these and then normalize by their sum so that we get a probability vector. And the nice aspect of this is that the loss function has a very simple form. If you do a calculation of taking these m class version and then translate it back into two classes, you will see that the m class versions is actually just an extension of the two class discussion that we've been making so far. And then the gradient has a very simple and straightforward interpretation so that we can very easily make these changes and make the gradient updates so that we can improve our weight matrix. As a neural network, the M class version is looks very similarly, except that instead of having just one of the nodes in the center for the different classes, we now have M of them, and we have the input weights as the input vector, and then the output vector. And the change here is that instead of using sigmoid, we're using the softmax or phi. And this setup I've introduced for a couple of different reasons. One of them is that it introduces most of the basics of the deep learning techniques, but also because it's equivalent to logistic regression. So if you've ever used a logistic regression package for machine learning in the past, this framework that we've described so far is exactly equivalent to that, and already quite useful. However, we're not yet at the level where we're using deep learning. And to motivate that, we're going to take a look at one basic and important concept in machine learning called linear separability, where tasks can if you again this is sorry this is a two-dimensional. This task is looking at a two-dimensional task, and we're trying to separate between the blue and the red dots. But linear separability refers to, can you draw a line that will separate between the two types that you're looking for. However, in most cases, we don't really have that. What we have is a task where you can't draw just a single line that will separate between them. And then one of the important aspects of neural networks is that if you have a network with only a single layer, you can only handle linearly separable tasks. However, once we start working on multi-layer neural networks, this network has 3 layers, then we get the ability to start handling tasks that are not linearly separable. In a multi-layer neural network, each layer has its own weights, and also each layer has its own activation function. The activation function we were using in the past, in previous slides, was either the sigmoid or the softmax. Usually, in a multi-layer neural network, we'll use a sigmoid or something similar like the hyperbolic tangent at each of the layers up till the last layer. And then in the output layer, we would use the softmax or something similar that would more closely addresses the task that we're looking for. And as we start having multiple layers, the neural network becomes essentially a universal approximator for functions in general. And it has the ability to consider interactions between the inputs, which then, as we get multiple layers, gives it the ability to start doing this feature extraction that then becomes so very useful. Training a multi-layer neural network uses a very similar setup to the single layer that we talked about a moment ago. The algorithm is what's called backpropagation, and it uses 2 different steps. The forward step calculates the outputs of each of the layers, while the backward step uses the chain rule, the calculus chain rule, to update the weights at each layer. And this is the first point where I'm going to not give all of the details, partially because there's quite a bit of finicky math that's involved, but also, and importantly, because the software packages that implement deep learning all have the ability to calculate this for you, so that it's not something that you have to implement yourself. And they've already handled not only the implementation, but also, importantly, all of the testing to get this the gradient calculation correct, so that you can then apply the stochastic gradient descent and make it not only correct but also fast. So this is, as you can see, one of the aspects that's important about neural networks is that we start with the basic concepts, but we start building and looking at them at a higher and higher level. Putting a whole idea together about multi-layer neural networks, there's many different things that you can modify, and these things are what then allow the neural network setup to be applied to different tasks or different data sets. These are called hyperparameters. For example, the network structure, such as the number and the size of the layers, which activation functions you're using, sigmoid and softmax. There's others like the hyperbolic tangent, but also what training setups are you using, initialization, and also the learning rate, loss function, how many training data points are you considering for every update, because it is a bit more efficient to use more than just one. But also, what point are you going to stop training? The calculation for the gradient, and also other more mathematical aspects to make sure that the process is well behaved and generalizes, are techniques that you will find in other introductions. And all of these can be optimized on a holdout set. So in addition to the training data, we usually will set aside a little bit of the data, and after every run through the data, we will do an evaluation to see whether the weights are continuing to produce better and better predictions that the loss is going down, and then allow us to stop training. But also this allows us to make modifications to these parameters so that we can then identify what setup will work best. So far, looks like I'm need to continue for just another couple of minutes here. Hopefully that will be okay. So far, what we've been discussing is a setup where we have just one input, even if it's a vector, and one output. But in working with text mining, we more frequently have variable length inputs. Quite often we have, let's say, a sentence, and we need to make predictions for all of them. This is another place where being able to consider neural networks at a higher level of abstraction is very useful. The main technique the first technique that is worth considering for this sort of a setup, say for this example, where we have an input of multiple words, say a sentence, then we have to do a prediction for each of them, is the recurrent neural networks. And the main idea here is that we have a hidden state that then we then use a network with a set of parameters to do the predictions for each time step. Of the way this works is that we for every time step we take the previous time step and also the input at that time step, and then we run that through a neural network layer. You can see the weights, and also the hyperbolic tangent is the typical activation function that's used. And then the output at that time step will then be, again, weights with softmax to get a prediction for that time step. These can be trained using the very same back propagation algorithm, just back propagating through time. That is, it will make predictions going forward and get the outputs, but then the backward pass will do calculate the error updates and the gradient for all of the time step, and then make changes to the network weights at each point. With recurrent neural networks, one of the main issues, there are two main issues. One of them is what they call vanishing and exploding gradients. The error has a tendency to either increase or decrease exponentially, which means that it either will get so small that we won't do any updates, it would be a vanishing gradient, or an exploding gradient, which then gives mathematical overflows. The other problem is that it's unable to remember information over many time steps. It has a tendency to get diluted as it goes through the network. One of the improvements to recurrent neural networks that improves on this is the long short-term memory network. And what this network does is that it has several different setups, several different networks within it that then give it more control over the cell state. This is the equivalent of the hidden state that's used in recurrent neural networks. And then it has these functions that allow it to learn what to add or what to forget from that cell state based on the inputs. And then this same cell is then applied at every time step. To give a quick example, with chemical named entity recognition, this is a paper from 2018 that provides a chemical identification system. Given an input that represents each of the words, we are looking for an output that then classifies whether or not the word represents a chemical or not. And what they use is a bidirectional LSTM. So they use one LSTM for the forward direction and one for the backward direction, and then combine the outputs. And then the output layer is, it's similar to softmax, but instead uses the most likely tag sequence by considering the interactions between the tags. This is already very high performing, but then we do have one issue, which is consistency. That is, the same word should usually receive the same tag. You can see the word cocaine here. It represents a chemical, and so it should receive the same tag. The solution to this is attention, where we use a weighted average of all of the outputs at all of the other time steps to as an input to allow us to identify some additional information that can then be useful for predicting the current word. And in this case, we use a similarity between all of the other words as the weight. So the way that works is by looking at a similarity function, could be cosine similarity or similar. And we then use a softmax over that. That's the phi we were discussing earlier. And then that is used as the attention, as the weight value. We then give the weighted average of all of the other outputs of that bidirectional LSTM layer. And then that is then used as the input to the TANH layer and then to the overall output. Using this attention is a small change to an already very good system, but it actually has the ability, in this case, it reduced the error rate by about 10%. So in conclusion, we talked about why deep learning is interesting. We talked about classifying single instances. Specifically, we went over a logistic regression and also how to do training. And then we took up a layer of abstraction to looking at structured classification, where we can classify sequences, including RNNs, LSTMs, and attention.